Then should we start? Hello, students.
Yes, sir. Hello. Hello.
Or we should wait for 2 more minutes to other to join.
Yes, audible, sir.
Should we start or we should wait?
Audible, sir.
Yes, now it is audible. Now it is audible. Hello.
Yes, sir.
Yes, sir.
Now it is audible or not?
Yes, sir.
Yes, sir.
Yes,
Ye-
actually the network is not
Audible.
good because you know the rainfall is very high. Now it is audible, no? Now it is audible.
Yes, sir.
Yes, sir.
Okay. So we should wait for 2 more minutes. That should the others should join. Then we will start. Yes.
Okay, sir.
Okay, sir.
Okay. So now we'll start, students. So many of the students have joined, so we'll start now. So today, so we have block number 5, estimation and gravimetry. So we have 3 units, 12, 13 and 14. So we'll go one by one today. First of all is your precipitation titrations. Precipitation titration. So these things we'll discuss today. Here we'll discuss precipitation and introduction, then precipitation titration, feasibility of precipitation titration, titration curves, major regions of precipitation titration curves, titration of Br minus with Ag plus, Cl minus with Ag plus, iodide with and chloride mixture with silver ion, factors affecting the sharpness of endpoint, indicators used in precipitation titration, Volar's titration equilibrium, Fajan's titration, and Moore's titration and its application. Okay, let's go one by one. First of all, in the block 4, you have learned redox titration and complexometry titration. And is the last block, which has 3 units. First unit deals with the precipitation titration, and second unit is with the gravimetric titration. And in the last unit, we will introduce the kind of instruments used in analytical analysis. Therefore, first of all, we will discuss about the precipitation titration. I can simply say it is the one in which the titrant forms precipitate with analyte. The titrant forms precipitate with the analyte. So we are going to have a precipitate. You know precipitation reactions. If I will ask you, then you can say example of it. For example, you add silver nitrate to barium chloride solution, you get barium chloride. So when you react with silver nitrate with barium chloride, you get silver chloride as the precipitate. You get silver chloride as the precipitate and barium nitrate. So this is a precipitation reaction. So precipitation reaction means reaction between two solutions, and there will be a precipitate of different colors. For example, as I have told you, if you add silver nitrate to barium chloride, you get silver chloride is a white precipitate and barium nitrate. But here you have two things. One is titrant, which forms precipitate with analyte. So whenever you are getting a precipitate, some difficulties in meeting these requirements must be exist to locate the endpoint. Precipitation frequently proceeds slowly and starts after some time. Many precipitates show a tendency to absorb and thereby co-precipitate the species being titrated or the titrant. So sometimes what happens? Sometimes the precipitation, precipitation more frequently occurs slowly. As it occurs slowly, it takes some time. Many precipitates show a tendency to absorb and thereby co-precipitate the species being used for titrate, for the titration or called titrant. The indicator may also be a function of appropriately at the endpoint. If a precipitate is highly colored, then visual detection of color at the endpoint may be possible, but even when a white precipitate is formed, the milky solution may still make location of the endpoint difficult. Due to these difficulties, precipitation reactions or titrations are not so popular in present day routine analysis. The major area of This application includes determination of silver and or halide by the precipitation of the silver salt. Argentometric titrations, we can say it is also, and determination of sulfate by precipitation of barium sulfate. So we'll discuss one by one. Okay, in this case, but at present there is an you know that there is an abrupt decrease in the analyte concentration and increase in the titrate concentration during the reaction. So when precipitation titration takes place, there will be a decrease in the analyte concentration and increase in the titrate concentration. Therefore, a pH of log analyte or pH of or log titrant versus volume of the titrant added typically gives an S-shaped titration curve with a break at the equivalence point. So remember, when we are drawing a graph between log analyte or log titrant versus volume of titrant, then we are getting a S type of curve. And you see the break points are there. These break points are called equivalence point. The end point determination of the equivalence point is found to be graphically analysis of the break or by indicators. Okay, one by one we'll go. First of all, feasibility of precipitation titration. So here you see that the reaction rate should be sufficiently rapid. Specifically, the titration dilute solutions, and in the immediate vicinity of the endpoint, the rate of precipitation may be imperfectly slow. Very slow precipitation takes place. To improve the rate of precipitation, it is sometimes beneficial to change solvent by adding alcohol or to raise the temperature. So sometimes as the precipitation reaction or precipitation titration is very slow, therefore you have to add a solvent or you have to add some alcohol or to raise temperature. By adding excess reagent and back titrating, it is possible to take advantage of more rapid precipitation in the reverse direction. By changing an endpoint method that does not require equilibrium to be reached in the immediate vicinity of the endpoint. Now, students, what you do here, first of all, important here is that the basic concept. The basic concept is that titration curve. So here, important thing is that whenever you are going to do a titration, for example, in this case, you've taken a titration of 100 ml of 0.1 m Ki with 0.1 m AgNO2 solution. So you see here, the example taken is here 100 ml of 0.1 m Ki, 100 ml of 0.1 m Ki with 100 ml of 0.01 m Ki with 0.1 molar silver nitrate as titrant. The reaction will be Ag plus I minus to give you AgI. Ag plus I minus to give you AgI. And the AgI product has a relatively low solubility product. AgI has a relatively low solubility product, as you know, because it is a sparingly soluble salt. So see, first of all, again, I will explain you that we are going to do a titration between 100 ml of 0.01 m Ki solution. So titrate, here is the titration between the 0.01 m Ki solution with 0.1 m AgNO3, 0.1 m AgNO3 solution. So reaction will be between Ag plus and I minus. Reaction between Ag plus and I minus. Remember, the reaction is between Ag plus and I minus. So whenever such a reaction takes place, the reaction between Ag plus and I minus, then you get AgI as a solid, as a precipitate. Remember, AgI solid, AgI solid is very sparingly soluble salt. It is not soluble so much. So the Ksp of AgI is nothing but Ag plus concentration into I minus concentration. And as you know, this value is a constant value. Its value is come to be 1.0 10 to the power minus 16. Then in 100 ml of 0.01 m I minus, there is how much of concentration of I minus? Now 100 into 0.01 equal to 1 millimolar. 1 millimolar of I minus. This requires the addition of 1 millimolar Ag plus to precipitate all the I minus, corresponding to a total of 10 ml of Ag plus to react the equivalent points. So what you do now here, now you do, there are three major regions of titration curve. One is prior to equivalent point, then second is at the equivalent point, and third one is beyond the equivalent point. First is prior to equivalent point, means before the equivalent point is reached. Then next is at the equivalent point, and third one is the beyond the equivalent point. So addition of 1 ml of Ag plus titrant corresponds to 0.1 millimole of added Ag plus. So by doing calculation, you can calculate Ag plus and I minus, and you can take the log of this. As I have told you earlier, that you have to take log of this, log of Ag plus and equal to I minus, equal root over of Kst. So log of Ag plus comes to be 8.0. Similarly, I minus also you can able to calculate. Then what you do the precipitation curve. You have to draw a curve. You can see the curve in your figure 12.1. 12.1, you can see the volume of AgNO3 titrant along x-axis and PAg along y-axis, or PL along y-axis. You can get a graph. Similarly, titration of Br minus with Ag plus. Again, you can have a S type of curve. You can see the equivalent point, before equivalent point, and after equivalent point. So three things are there in the graph. You can notice it. Next one is titration curve, titration of Cl minus with Ag plus. Similarly, you can get the titration curve, and also titration of iodine and chlorine mixture with silver ion. You can see there are two types of curves are there. One is due to Ag iodide ion, and second one is due to chloride ion. And you can see the graph also. It is also a graph of two graphs mixing together like this. You can see the graph. So now, as you have seen that it is simply based on the concentration of the ions produced during titration and its reaction. So now question arises, factors affect the sharpness of endpoint. Endpoint may not be sharp. So how this endpoint has been affected? These things now we are going to discuss it. Look at this. Both the magnitude and the sharpness of endpoint break influence how equivalence point can be estimated. So equivalent point depend on the sharpness of the endpoint. Therefore, it is important for us to examine the variables that can influence the shape of the titration curve. The properties of indicators also affect how well equivalence point can be estimated. The properties of indicators also affect how equivalent points can be estimated. Okay. Estimated. So we will go one by one also. After this, we'll discuss all these things also. The silver ion concentration before the equivalent point depends partly on the original concentration of bromide ion, while after the equivalence points, it depends partly on its own original concentration. There is most important factor which I'm discussing it here now. First is the silver ion concentration before the equivalent point depends partly on the original concentration of bromide ion, but after the equivalent point, it depends on its own original concentration. As a result, high concentration of analyte and titrant produce larger and sharper endpoint. So remember, if the analyte and titrant have high concentration, then you get sharper endpoint. You get very sharp endpoint. Means immediate you get the endpoint. Endpoint break, sharper endpoint break, then do with low concentration. So if you have high concentration of titrate and analyte, then you can able to get a very sharp endpoint. Okay, then you have to go to completeness of the reaction. See, the completeness, the equilibrium constant for a reaction in which a precipitate is formed usually is just the reciprocal of the solubility product constant for the precipitate. So a very interesting thing. For example, you have Ag plus and SCN minus, thiocyanate ion. Then you have AgSCN minus. So KSP is equal to Ag plus into SCN, KSP is equal to Ag plus concentration into SCN minus concentration. Then K equilibrium is inverse of it. So K equilibrium is equal to 1 by KSP. K equilibrium is equal to 1 by KSP. Remember it. K equilibrium is equal to 1 by KSP. This is the relation between K equilibrium and your and your KSP. Experimental measure. Okay, this is indicators for precipitation reactions. Now we'll discuss about indicators of precipitation reaction. Now we'll discuss about indicator of precipitation reactions. So first of all, see any type of titrations, you need an indicator. So your indicator is very important to judge the end point. So here also the same thing happens. Titration curve just described above, as we have described above. So a abrupt change in titrate concentration means there will be a long change in the concentration of titrant, thereby an abrupt fall in analyte concentration at the equivalent point. So at the equivalent point, the concentration of analyte undergo a abrupt change, means sudden change. This is the reason why obviously a reagent that responds to the abrupt rise in analyte concentration at the equivalent point can be employed as an indicator. So therefore, remember, as I've told you that there is an abrupt change in the concentration of analyte. So we have to use an indicator of similar indicator. Then only you can able to judge the equivalent point. Several methods have been adapted for showing end point in precipitation titrations. The better known of the have been developed by titration involving Ag plus. So in Ag plus titrations we will discuss one by one, and formation of a tolerability. Okay, so we'll discuss one by one. First of all, the Volhard method. So this Volhard method, first I can say Volhard method is for chlorides. Volhard method, chlorides are first precipitated with excess silver nitrate. So remember, if you use excess silver nitrate, then AgCl is precipitated. So here, remember, your AgCl is going to be precipitated if you are using excess of silver nitrate solution against potassium or sodium thiocyanate. So potassium or sodium thiocyanate means formula is KSCN, potassium thiocyanate, plus your Ag, and you are adding silver titrated against potassium sodium thiocyanate, and excess of silver nitrate was added. Then now you see formation of a color complex, that is FeSCN2 plus, may be used as to indicate the end point. So here the end point is FeSCN2 plus. FeSCN2 plus. Ferrous thiocyanate is the indicator used in this case, and the titration reaction is as follows: Ag plus SCN minus equal to AgSCN solid. And you see that when ferric is present in the solution, the following reaction occur at the end point. Fe2 plus SCN minus gives rise to FeSCN2 plus. It's a red complex. So the complex is red in color. So the end point is readily observed by the intense red color of FeSCN complex, in order for this means of indicating endpoint to work. So in this way the endpoint works. So during the Volhard method, we are using FeSCN2 plus as indicator, and the reaction between Ag and SCN to give you AgSCN as a precipitate. This indicator is used. The formation of FeSCN2 plus forms the basis of the Volhard method. So when Fe3 plus combines with SCN minus, then it gives you FeSCN2 plus, a red precipitate. This formation of FeSCN2 plus is the basis of Volhard's method. The Volhard's method titration can of course be used for the determination of Ag plus by titration with SCN minus. It can also be employed for the determination of Br minus and I minus by adding an excess of standard Ag plus and back titrating with standard SCN minus. So anyway, the important thing here, is AgCl plus SCN minus gives rise to AgSCN plus Cl minus. So this is the way we are verifying through Volhard's method and the titrate, and the indicator is FeSCN2 plus. So Fe and SCN2 plus. FeSCN2 plus is the indicator. Okay. Then we go to Volhard's titrant equilibrium. Volhard titrant equilibrium. The Volhard titration endpoint is not heavily dependent on Fe3 plus ion concentration. Between Eth to Eth, it can be used. So typical, the concentration of colored at this much must reach this before it is visually detectable by the average individual. Therefore, remember the Volhard titration method is not heavily dependent upon the Fe3 plus ion concentration. Iron 3 concentration between 0.002 and 1.6 molar can be used. So in this case, remember the concentration should be in between 0.002 molar to 1.6 molar. 0.002 molar to 1.6 molar, you have to use it. Okay. Then equations are there, equilibrium reactions are there. You can read yourself how the equilibrium reaction takes place. So no need to discuss this thing because it's a practical application. The next one is Fajan's method. Fajan's method is a direct titration of chloride with silver ion from silver nitrate. It is a direct titration between chloride with silver ion from silver nitrate. Means you are silver nitrate you are using, from which Ag plus comes and Cl minus combines with it to form AgCl solid, having very low solubility product KSP is equal to 1.8 and therefore minus 10. Then how absorption indicator works here? We discuss this one. Absorption indicators are dyes that absorb or dissolve from the surface of a precipitate near the equivalence point in a precipitation reaction titration. To be useful for endpoint indication, this must result in a distinct change in color either on the surface of the indicator precipitate or in the dyes in which it is suspended. Therefore, absorption indicator means absorption indicator means absorption indicators are dyes that absorb or dissolve from the surface of a precipitate. So we can discuss this also here. The method of endpoint indication is sometimes called Fajans method after its originator. Means Fajans has applied this method to estimate the amount of chloride present in a solution. Hence, it is called Fajans method. And here the best known absorption indicators are fluorescein, 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 and fluorescinate anion. It's a reversible reaction, equilibrium reactions, you can say. So the best known indicator, absorption indicator, is fluorescein, which is used to indicate the equivalent point in titration of Cl minus with Ag plus. So when we are doing titration of Cl minus with Ag plus, then we are using this absorption indicator, name is fluorescein. So we are using this fluorescein as an absorption indicator. And it's looking like a structure you can see in the diagram the book, a benzene ring having a OH group, alcoholic group, then again a benzene type of ring, but having 2 pi bonds oppositely faced, then again a benzene having OH group, then below you can have a ether type of linkage and a ketone type of linkage like this. So fluorescinate anion has a yellow-green color. So when fluorescinate undergo ionization in presence of H plus, then it gives you fluorescinate ion, which is an ion which is green yellow color. It's a yellow green color solution. So all the fluorescinate anion forms an intensely colored precipitate with Ag plus. It is used as an indicator or at concentration that do not exceeds the solubility product of the silver fluorescinate salts. So you can see the reaction: greenish yellow AgCl dot Ag plus A minus. It comes from fluorescinate anion. It's pink in color, then it gives you AgCl dot Ag plus and A minus. When Cl minus is titrated, okay, so we can discuss it also that during this titration, that forms at the end, at the point of addition of Ag plus to the solution just prior to the equivalent point, as a result of localized excess silver ion disappears, the solution becomes completely mixed. Okay. Okay. The next is Morse titration. Next one is Morse titration. The formation of a second colored precipitate at the end point can be used for the determination of end point. Okay. In Morse method, we are using brick red silver chromate, Ag2CrO4. So in Morse method, we are using brick red silver chromate, Ag2CrO4. Calculation of endpoint equilibrium in the molar concentration. The prior to the endpoint in the Morse titration, the Cl minus analyte is precipitated by the Ag plus titrant. According to the following reaction, Ag plus Cl minus AgCl solid is a white precipitate, and the end point is as the end point is approached, the concentration of Cl minus in the solution becomes quite low, and the value of Ag plus limited up to the end point by Ksp of AgCl rises steeply. As this occurs, the solubility product of Ag2CrO4 is exceeded, and the following reaction takes place. 2Ag plus CrO4 2 minus Ag2CrO4. Remember, the concentration of Ag plus and Cl minus equal. It is a sparingly soluble salt, and is equal to 1.35 and the minus 5 molar. So Ksp can be easily calculated for Ag2CrO4. As you know, Ksp is equal to Ag plus to the power 2, CrO4 to the minus 2 is equal to 1.2 and the minus 12. So by doing calculations, you can able to get the concentration of CrO4 2 minus ion. The indicator blank is the Morse chloride titration. Indicator blank. Next is applications. Application. We'll go to applications first of all, students. The most of the applications of precipitation titration are based on the use of a standard silver nitrate solution. So in each case, you need silver nitrate solution. Table 12.1 lists some typical application of argentometry, means silver, based on estimation based on precipitation and gravimetry. In many of these methods, the analyte is precipitated with a measured excess of silver nitrate, and this step is then followed by a Volhard titration with a standard potassium thiocyanate. Okay. Both silver nitrate and potassium thiocyanate are obtained in primary standard. The latter means the potassium thiocyanate somewhat hygroscopic, and thiocyanate solution are ordinarily standardized against silver nitrate. Both silver nitrate and potassium Thiocyanate solutions are stable indefinitely. They are stable solutions and they remain as it is indefinitely without having any chemical reaction. Both, okay, silver nitrate is a remarkably useful reagent for both titrimetry and gravimetry. Remember, silver nitrate is a remarkably useful reagent for both titrimetry and gravimetry. Both it is used for gravimetry and titrimetry. The silver nitrate is remarkably used for gravimetry and titrimetry. Its greatest drawback is its cost. Silver nitrate is very, very highly cost. It's silver nitrate. Silver nitrate cost is very high, which fluctuates widely with the world price of silver. The high cost requires that considerably care must be exercised to minimize the quantity of silver sample so that dilute solutions or small volume of silver nitrate are needed. In addition, the silver salt formed in the analysis and any reagent remaining afterwards would be collected for the subsequent processing to recover the silver or perhaps to convert it to silver nitrate for reuse. Okay. Typical argentometric precipitation methods. Typical argentometric precipitation methods. Substances determined ASO4 3 minus, Br minus, I minus, CNO minus, SCN minus. Endpoint is Volhard. Means which method you are using to calculate the endpoint. One is Volhard, one is by modified Volhard, and next one is electroanalytical by absorption methods like this. So Volhard is mainly commonly used, and otherwise it is modified Volhard also used. So endpoints you get according to the method you are using. Removal of remarks is there. Removal of silver salt not required. Removal of silver salt required before the back titration of excess Ag plus. So depending on the substance, the titration method varies. Okay. Change in the titrant and analyze the precipitation reactions or precipitation method varies. See, you can take Br minus and Cl minus. Then nothing to be worried, but if you got Br minus, Cl minus, and SNO, SeO3 2 minus, selenium oxide 2 minus, then it is an absorption indicator. Similarly, zinc 2 plus, F minus. Then you can get a modified Volar method, precipitation as Zn mercury SCN whole per filtration, dissolution in acid. Yes, so the methods you remember it, no need of it. Then we will discuss some questions. State the condition for functioning of absorption indicator. State the condition for functioning of absorption indicator. So you see here, precipitation frequently proceeds slowly or start after some time. Many precipitates show a tendency to adsorb or thereby co-precipitate the species being titrated or titrant. This will come in examination. Then what happened in this case now? The indicator may also be adsorbed on the precipitate form during the titration and thereby unable to function appreciately or appropriately at the end point. If the precipitate is highly colored, visual detection of color change at the end point may be impossible, highly colored. But even when a white precipitate is formed, the milky solution may still be make location of the endpoint difficult. So if the endpoint is difficult to see, if you have the solution which is very highly colored, or even if white also, because it's very much to look in through white there where work has been done and why it is pending. First question. Second question is what are the applications of precipitation reactions? To improve the rate of precipitation, it is sometimes beneficial to change solvents. That is by adding alcohol or to raise the temperature by adding an excess amount of reagent and back titrating. It may be possible to take advantage of a more rapid precipitation in the reverse direction. Okay. Then next was okay. Then we go to that's all about your unit 12. No much, no much things left in the topic. So we can take 5 minutes break. Then we can start the next unit. Yes. So students, can we take a break for 5 minutes?
Okay, sir.
Gitanjali.
Okay,
Okay.
sir.
Thank you.
Okay,
Thank
sir.
you. Okay. Okay, now again we will continue our study. We will go to unit 13, that is gravimetric titration analysis. Discuss one by one. Here you will be able to know gravimetric analysis as a general introduction, supersaturation and nucleation mainly. Then superannuation, release a rate of precipitation, co-precipitation, absorption on the surface of the particle, occlusion by incorporation of foreign bodies, role of precipitation for separation of dyeing and ignition precipitates, washing of precipitates, organic precipitates, regular with some important functional groups, advantage and disadvantage, summary. So we'll discuss one by one. Gravimetric analysis means there are two basic approaches. There are two basic approaches to quantitatively analyze. One is by measurement of volume, and other one is based on measurement of weight. So here the two important terms are volume and weight. In titrimetry, the volume of a solution of accurately known component concentration required to react quantitatively with the solution of a substance known concentration required to determine in transferred to a pure suitable solvent. The separation of elements which can converted to be determined in transfer to a particular substance. So now we'll discuss its effect. Nucleation. Nucleation is a physical change. A solution starts to precipitate. Starts to So we'll discuss this method of gravimetric. So first of all, as I've told you that during the nucleation is a physical reaction which occurs when component in a solution starts to be precipitated. In a simple example of nucleation, supersaturated sugar water is used make rock candy with the sugar crystals nucleating and growing into crystals. So before discussing more about nucleation, it may be important to know the dependence of solubility or particle size. The solubility of a substance at a given temperature in a given solvent is the amount of substance dissolved by a known weight of solvent when the substance is in equilibrium with the solvent. The identification of solubility increases greatly with decreasing particle size. In gravimetric analysis, large particle size precipitates they are less prone to surface absorption solid formed by precipitation varies largely. At one end, there are particles of the diameter of the -7 to the -4 cm are so no tendency to settle down from solutions and cannot be easily filtered. At the other end, there are particles with dimension of the order of tenth of a millimeter or greater. The dispersion of such particles in liquid phase is known as crystalline suspension. A particle of crystalline suspension quickly therefore, it is known that different experiments variably influence the particle size. Some of the important ones are precipitate solubility, temperature, reactant, concentration, and rate at which they are mixed. The net effect of these variations can at least be qualitatively accounted for by a single property of the system known as relative supersaturation. Relative supersaturation. Relative supersaturation. Then what do you mean by supersaturation? A supersaturated solution is one which contains greater concentration of the solute than permitted by the equilibrium solubility at the temperature under consideration. So if you at a particular temperature, if you dissolve some solute to a particular solvent, then solute may dissolve and a point will come, there will be no more solute can dissolve, we can say it is saturated. But with increase in temperature, you can increase the solubility. But again, it is to an extent, and that solution is called super saturated solution. Essentially, super saturated solution is an unstable state just before the precipitation begins. This unstable state may be brought to a state of equilibrium by addition of a crystal of the solute or some other substance or by mechanical means, naming shaking or stirring. Very interesting is this one, super saturation. First of all, to measure, first of all, you have to S can be increased by making use of the factors, namely so first of all, the He, the precipitate is usually, so there are the factors that affect solubility are precipitate is usually carried out in hot solution because the soluble বাগে লেগেছে না Okay. So next one is in generally recommended to carry out precipitation from dilute solution and the reagent is added slowly with constant stirring. The slow addition of the reagent results in the formation of fewer number of primary particles which grow on more material precipitates. Constant stirring helps in coagulation of colloidal particles and proper crystal growth of the precipitate. Stirring also helps in the distribution of the precipitant in the whole bulk of the solution. And one more important factor is to increase the solubility of the addition of soluble suitable reagent is often recommended. This also leads to the formation of large primary particles. So these are few factors which affect the rate of precipitation. And the formula is initial velocity of precipitation is proportional to Q minus S by S, where Q is the concentration of the at an instant and S is the equilibrium solubility. Okay, then digestion of the precipitates with mother liquor. In order to improve the nature of the precipitate, the above approaches are adopted. during the actual precipitation process. However, there is one other recourse available after the precipitation. That this makes the use of the first mentioned things. The material of smaller things, smaller precipitates is allowed to stand in contact with the mother liquid frequently at elevated temperature for some time before filtration. The smaller particles go into solution, making it supersaturated with respect to larger particles. The equilibrium with respect to them to grow even larger. The process is often termed as Ostwald's ripening or ripening. It has been observed that the digestion does not significantly improve the nature of cloudy precipitate like AgCl or gelatinous precipitate like FeOH whole 3. This happens when the compound is either very insoluble or the particles do not differ much in size. However, digestion at elevated temperatures become before filtration is successful in increasing the particle size of crystalline precipitates like barium sulfate and calcium oxalate. Then we'll go to co-precipitation. Then we'll go to co-precipitation reaction. Then remember, precipitates separating from a solution are not as a rule pure, but contain larger of foreign substances, including mother liquid. The precipitates may contain varying amount of impurities depending upon the nature of the precipitate and the conditions of precipitation. Precipitates separating from solution are not as a rule pure, but contain large amount of foreign substances, including mother liquid. The precipitates may contain varying amount of impurities depending upon the nature of the precipitate and the conditions of precipitate. The contamination of the precipitate by substances that are normally suitable, soluble under the condition of precipitate is called co-precipitation. So what is co-precipitation? Remember this one, very interesting thing. The precipitate may contain varying amount of impurities depending upon the nature of the precipitate and the conditions of precipitation. The contamination of the precipitates by substances that are normally soluble under the condition of precipitation is called co-precipitation. The precipitation so happens may also undergo precipitation under some suitable impurities, and we can call it as a co-precipitation. Uh, contamination contamination as a result of co-precipitation should be distinguished from contamination as a result of purely chemical precipitation. A typical example of co-precipitation is encountered when barium chloride is added to a solution of potassium sulfate. Barium chloride added to potassium sulfate. Then students, what do you get? Barium chloride, BaCl2 plus K2SO4. You get what? A BaSO4, barium chloride plus K2SO4. You get barium sulfate plus KCl. You get barium chloride plus KCl. So here precipitate is potassium sulfate. So when barium chloride, so a typical example of co-precipitation is encountered when barium chloride is added to a solution of potassium sulfate. Then barium sulfate is formed after washing. to contain greatly or lesser amount of potassium sulfate in spite of the fact that the salt is freely soluble under the circumstances. So co-precipitation predominantly but prominently take place by the two mechanism. So co-precipitation predominantly or prominently takes place by two mechanisms. By two mechanisms. Eh, that is, one is called adsorption at the surface of the particle, and second is called occlusion by incorporation of foreign ions as solvents. So method of minimizing co-precipitation. Method of minimizing co-precipitation. How to minimize the co-precipitation during precipitation? So there are two methods or two steps, or you can say two important generalization needed for minimizing co-precipitation. One is precipitation should be carried out from dilute solution, keeping in mind that the solubility, the time required for filtration, and the subsequent operations to be carried out with the filtrate. So three things you have to be remembered here. Precipitation should be carried out from dilute solution, keeping in mind the solubility, the time required for filtration, and the subsequent operations to be carried out with the filtrate. If precipitate is formed by mixing very concentrated solution at room temperature, it separates out more or less as a fluctuated colloid, which is likely to be contaminated by surface adsorption. And second one is the reagent should be mixed slowly with constant stirring. The reagent should mix slowly with constant stirring. This is how we can keep the degree of supersaturation low, and will be able to get larger crystals. Larger crystals have lesser surface adsorptions. Okay. Then precipitation should be carried out from hot solution permit. Since solubility increases, the degree of supersaturation decreases. Remember, solubility increases means the degree of supersaturation decreases. Coagulation of the precipitate is assisted, thereby reducing the sol formation. The velocity of the crystallization is increased, thus leading to better formed crystals. Crystalline precipitates be distinguished within the other liquor as long as practical, except where post precipitation must may occur. Digestion of the precipitate may be done by leaving the precipitate in contact with the mother liquor either overnight or on a steam bath or sometime. During digestion process, crystals with larger surface area and more prone to adsorption go into the solution and the corresponding material reappears on large crystals. It may be again emphasized here that the digestion has little effect on upon amorphous and gelatinous precipitates. The nature of the precipitates is hardly improved. Role of co-precipitation for the separation of tracer quantities. We'll discuss now. The role of co-precipitation for the separation of tracer quantities. We have seen that co-precipitation is detrimental as far as the purity of the precipitate is concerned, but it can be very useful for the separation of tracer quantities of radioisotopes. Radioisotopes produced by nuclear reaction are usually present in extremely small quantities, and ordinarily precipitation procedures generally falls at such extremely small quantities and at low concentration. The separation of unweighable amount of tracer material from macro quantities of targeted material by co-precipitation usually involves two steps. First, for the role of carrier absorption, use carrier substance that can be separated from the tracer usually in subsequent operations. Generally, the tracers are co-precipitated by surface adsorption on unspecified carriers. Next, we go to post precipitation. Next, we'll go to post precipitation. Can you take 2 to 3 minutes break, students?
Yes, sir.
Hello, Ojas.
Yes, sir, sure.
Okay. Okay, next we discuss about post precipitation reaction. Co-precipitation is important for as far as the contamination of precipitate with foreign particle is concerned, but there is another process called post precipitation which makes a precipitate impure. So post precipitation makes a precipitate impure. In this case, as the name suggests, the primary precipitate separates out in a pure form in the second phase of foreign substance which is slightly soluble form afterwards. The second phase is therefore not co-precipitated but called as post-precipitated. It is called post-precipitated. Post-precipitation can occur only when the supernatant is supersaturated with respect to some components which crystallizes fairly slowly. Therefore, remember that students that post precipitation makes the process simply impure. So, if you are getting a pure precipitate after post precipitation, it becomes again impure. Therefore, in the precipitation of calcium as oxalate, in the presence of magnesium, a small amount of the latter is co-precipitated with the calcium oxalate. However, if suspension is digested for a long time, so magnesium oxalate also appear on calcium oxalate. The longer the precipitate is allowed to stand in contact with the solution, greater is the post-precipitation of magnesium oxalate on calcium oxalate. Then we can now, I will now explain you an example of post-precipitation when H2S is passed through 0. Sorry, when H2S gas is passed through zero point 0.2 normal H2S per solution containing copper 2 plus ion, a little amount of zinc 2 plus ion is added also. Copper sulfide will precipitate fast without carrying zinc. So copper sulfide will precipitate without having any zinc. It means that there is not only there will not be any co-precipitation. However, if the precipitate copper sulfide is left with zinc ion in solution, zinc sulfide is precipitated and the copper sulfide precipitate. The strong promoting agent of copper sulfide is due to the fact that it has strong adsorptive property towards hydrogen sulfide and other sulfide. So copper sulfide has strong adsorptive properties towards H2S. So copper sulfide has strong adsorptive property towards H2S. Now we'll discuss differences in co-precipitation and post-precipitation. So the main difference, there are three differences. One by one we'll discuss. First one is if the precipitate is left in connect with the mother liquor, the contamination increases with time. In post precipitation, the contamination increases the faster the solution is extracted by either the mechanical or by thermal means. The reverse is generally the case with co-precipitation. In case of post-precipitation, the contamination increases with the faster the solution is extracted by either the mechanical or by thermal means. The reverse is generally the case with co-precipitation. The reverse is generally with the co-precipitation. Next, we go to precipitation from homogeneous solution. The major objective of a precipitation reaction is the separation of pure solid phase. So the main objective of precipitation is the separation of pure solid phase. In order to obtain a solid with minimum contamination, it's desirable to produce large, well-defined crystals rather than microcrystals. So precipitation, if results in the formation of well-defined crystals, then microcrystals, then we can say that the separation of solid phase occurs. In other words, compact and dense precipitate instead of a gelatinous precipitate is required. We need a compact and dense precipitate instead of a gelatinous precipitate. Next is the guideline to be used in the precipitation to precipitate. In the preparation to precipitate with desired physical characteristics were offered by one women. The key lies in the fact that the degree of super saturation should be kept minimum. The important thing here is that the degree of supersaturation should be kept minimum. This is the primary condition for precipitation from homogeneous solution. Secondly, once you make the supersaturation at minimum, it will lead to fewer nuclei and material will grow on them. Ideally, the precipitating reagent should be added in the form of successive small increments until its concentration just reaches the threshold value. The problem has been sorted out by slowly generating the precipitate by a homogeneous chemical reaction within the solution instead of adding the precipitate extensively. Okay. And more things we'll discuss in the coming class. So only 10 minutes left. So any doubts you can ask me. Can tomorrow I can take class or it is not possible to take tomorrow class? Can anyone say? One more class required. So can tomorrow I can take class or not? Or it is not allowed to take class on tomorrow?
How do we know, sir?
Then tomorrow I can take class or not? No. I don't know. It is possible to take class or not. That's what I'm asking. Is it allowed to take class or not? Because tomorrow I want to end it. Can I talk to the regional director, the deputy director, and I can confirm you now?
Yes, sir, will do.
Okay, I'm just calling him and then I'm confirming you. Okay. Okay.
Okay, sir.
Hello students. Hello. Hello.
Okay, sir.
Yes, tomorrow I can take class from 4 to 6 p.m. 4 p.m. to 6 p.m.
Okay,
No
sir.
problem. Please
Okay,
tell
sir.
everybody because otherwise I will inform here that tomorrow class will be from 4 to 6 p.m. If yes, then I will create the link for all of you at 4 p.m. to 6 p.m.
Please send the link, sir. Thank you.
Tomorrow class from 4 p.m. because tomorrow after the last class I will take my last class 4 p.m. to 6 p.m. If yes, please say yes. If you agree, please say yes. And inform all. Okay. Then tomorrow class will be from 4 p.m. to 6 p.m. Accordingly, I will tell the IGNO person to create the link for all of you, and you join at that link at sharply 4 p.m. And tomorrow I will complete the block 5 last unit. Okay. Yes. I will send the link to all of you. No problem. Okay. Okay, thank you very much. So please inform all that tomorrow you have class from 4 to 6 p.m. Accordingly, I am informing the IGNO person, Tapan Babu, and he will create the link for all of you. Okay. So only 1 minute left. I thank you very much, all of you, that we have today we have attended all the classes, all the my class, and we have discussed about the precipitation titrations and gravity titrations in details, and more things in the tomorrow class. Okay. Thank you very much.
Thank you, sir.
So tomorrow class timing is from 4 p.m. to, again I'm writing tomorrow from class from 4 p.m. to 6 p.m. evening. Okay, thank you very much. Thank you. Thank you all.
Thank you, sir.
They are writing election. हाँ सद्य के लिए ऑफिस बहुत सीधा हो जाएगा. Thank you very much. Thank you.